Welcome back to the Deep Dive. Today we're getting into a stack of source material you sent us, and it's all focused on the real nuts and bolts of network failure.
Specifically, how expert engineers troubleshoot IPv4 routing when, things just stop working.
That's right. Our mission today is all about problem isolation. We're looking at guides for those foundational tools: ping, traceroute,
Telnet and SSH. But this isn't just a list of commands. It's really about the thinking behind them.
We want you to walk away with a clear picture of what a command actually confirms, and maybe more importantly, what it rules out when the network goes down.
Exactly. We're testing the IPv4 data plane, basically. Can packets actually get from point A to point B? And what's great about these sources is the perspective they offer.
Yeah, they really highlight how many different things have to work perfectly all at once just for one simple connection to succeed.
So let's start with the one everyone knows, but maybe doesn't fully appreciate. Ping.
The first command anyone ever types. But the core question is, when a ping succeeds or when it fails, what is that precisely telling us?
Well, ping is so fundamental because it's not tied to any application. It doesn't rely on TCP or, any higher level protocols.
You mentioned it's a layer 3 tool. Does that mean it just bypasses TCP and UDP completely? What's it actually using under the hood?
It uses the Internet Control Message Protocol, ICMP. And yes, ICMP operates directly at layer 3, the network layer.
Okay.
The command sends what's called an ICMP echo request. If the destination gets it and is working, it sends back an ICMP echo reply.
So because it's this dedicated control protocol, its success is like the most basic confirmation of connectivity you can get, independent of any web server application.
Exactly right. A successful ping confirms the whole loop. The request made it all the way from the source to the destination.
And the reply made it all the way back, the full round trip.
Precisely. And when you run this on, say, a Cisco device, it's got a default behavior. It'll send 5 of those echo messages, and it waits about 2 seconds for each reply.
And that's where we get those classic little symbols in the output.
Famous ones. An exclamation point for success and a period means it timed out. A failure.
But the sources point out this little quirk that can save a junior engineer a lot of stress.
Oh, absolutely. This is one of the best time-saving tips in the material. It's what I call the one-dot phenomenon.
The first ping fails, but the rest work.
Yes. You see a single dot, then 4 exclamation points. So
yeah.
It looks like there's a problem, but a lot of the time, it's completely normal behavior.
So what's actually happening there? Why would the very first packet time out?
It almost always comes down to one thing. ARP. The Address Resolution Protocol.
Oh.
If your router hasn't talked to that specific host recently, it knows the IP address, but it doesn't know the hardware MC address. It's missing from its ARP table.
So it has to pause everything to figure that out first.
Right. It sends out an ARP request. Who has this IP address? And it has to wait for the reply. That tiny delay is often just long enough for the first ICMP echo to time out.
But once it gets that ML address and pops it in the ARP table,
the next 4 packets fly through without a problem.
That's such a valuable piece of context. It immediately tells you, don't go digging through routing tables. The issue was likely just local layer 2 address resolution.
Exactly. Now let's use that successful ping. A common scenario is that a user's computer, let's call it host A, has a problem, but you can't actually get on that machine to test.
So the strategic move is to test from the closest router, the default gateway. Let's call it R1. You log into R1 and ping the destination, host B.
And if that ping works, if R1 can successfully ping host B, the amount of information you get is just massive. You've just ruled out a huge list of potential problems.
So what's on that list? What if we confirmed with that one success?
Well, first and most obviously, IP routing. It's confirmed. R1 has a working loop-free route to get to host B.
And crucially, a host B must have a working route to get back.
Right, a return route back to R1's source IP address. So layer 3 is good, end-to-end. But people often forget it confirms the lower layers, too.
Of course. For that packet to move at all, the physical links have to be working.
Every single step. For layer 1 and 2, we know all the physical interfaces are up, any WAN circuits are working, no duplex mismatches, things like that.
It also tells you about the switching, right?
It confirms all the switching. Any LAN switches in the path must have learned the right ANCA addresses. And protocols like Spanning Tree Protocol, SDP, must have their ports in a forwarding state. If a port was blocking, that ping would have failed instantly.
And what about the things you can't see? The security policies that can silently drop packets?
Yes. The ping success guarantees that your security didn't interfere. Any IP access control lists, ACLs on the routers, They must not be blocking ICMP.
And even layer 2 security, like port security on the switches.
Also confirmed, the fact that the packet got through validates your entire security configuration for that path. It's an incredible amount of information.
So one command confirms routing, physical links, switching, security, and ARP. It lets you stop looking at the network path and start focusing on the end devices.
That's the power of isolation.
Yeah.
But this leads us to the big limitation of a standard ping.
Wait, how can it be limited if it just confirmed all of that? What could it possibly be misrepresenting?
Because a standard ping from a router uses its outgoing interface IP address as the source.
Okay, so if R1's packet leaves through its WAN port.
Let's say that port's IP is 172.16.4.1. The echo reply from host B is addressed to come back to that specific WAN address.
Ah, I see the trap. The original user, host A, is on the LAN subnet, maybe 172.161.0.
And that standard ping never actually tested the return route back to the user's LAN subnet.
So the path back to the router's WAN link could be perfect, but the route back to the actual user's part of the network could be completely broken.
And you wouldn't know it. That's why we need the extended ping.
So this is how you force the reply packet to take the correct path back, to fully test the reverse route that the user's traffic would actually take.
Exactly. The extended ping command lets you specify a different source IP. You tell R1, hey, don't use your WAN IP, use your LAN interface IP as the source.
The one that's in the same subnet as host A.
Right. Now, when the packet gets to host B, the reply is addressed back to R1's LAN IP, forcing the network to use the route that leads to the user's actual subnet.
That is a subtle but absolutely critical distinction. So what happens if you run these two tests and get different results?
And this is where you find the classic mistake. If a standard ping of a local host works fine, but an extended ping of that same host fails.
What does that point to?
The problem is almost always the host's own default router setting.
How does that one setting cause this specific failure?
Well, think about it. When the extended ping source is R1's LAN IP, host B sees the packet as coming from its own local subnet. It doesn't need a gateway to reply. It can just send an ARP and reply directly.
So a standard ping can work even if the host has the wrong default gateway or no gateway at all.
Exactly. But the extended ping forces the host to send the reply to a different subnet, the one the router's other interface is on. To do that, the host must use its default gateway setting correctly. If that's misconfigured, the packet dies right there.
That is a brilliant diagnostic trick. You're using the router to find a configuration error on a host machine.
It's an elegant way to confirm the layer 3 settings on the host itself.
Now, before we move off ping, there are a couple of other uses, right? Like testing DNS?
Absolutely. You can ping a neighbor on the same LAN. If R1 can't ping host A on its own subnet, you immediately know the problem isn't routing, it's local. A bad cable, a switch port error, maybe an IP address mismatch.
And then there's name resolution. If I type, say, ping host B instead of ping 172.16.2.101.
You're testing something totally different before the first ICMP packet even gets created.
I'm testing the domain name system, DNS.
Right. The device has to resolve that name, host B, into an IP address first. This is one of the fastest ways to tell a routing problem from a naming problem.
So the key diagnostic tip is if the ping by name fails.
But then you immediately try it with the IP address, and it succeeds.
The problem is DNS. Guaranteed. Something is wrong with the client's DNS settings or the server itself.
And you can stop worrying about routers and links.
Okay, so ping tells us if it works, but if it doesn't, the next question is, where did it break?
And that brings us to our second powerhouse tool, traceroute.
Traceroute is what maps the journey hop by hop.
It identifies every single router in the forward path. And its power comes from really exploiting a feature that was designed for network safety, the time-to-live field in the IP header.
It's amazing how engineers basically turned a failure mechanism into a diagnostic tool. How does messing with the TTL map the route?
So the TTL is just a counter. It starts at, say, 64 or 128. Every router that forwards a packet has to subtract one from the TTL.
And if the counter hits 0?
If a router gets a packet and decrements the TTL to 0, it is required by the protocol to discard the packet. But critically, it also has to send an ICMP message back to the source.
An error message.
The TTL exceeded message. And traceroute completely exploits this.
It weaponizes that notification.
It does. It starts by sending its first packet with a TTL set to just 1.
So it's designed to fail at the very first router.
Exactly. The first router gets it, drops the TTL to 0, discards it, and sends back that TTL exceeded message. The sort IP of that reply message identifies the first hop to the engineer.
And then it just ramps up the TTL value systematically.
Right. The next packet goes out with TTL2. The first router drops it to 1 and forwards it. The second router drops it to 0 and sends back the error message, identifying the second hop.
So by repeating this, TTL 3, 4, 5, and so on, it builds a complete map of the path, hop by hop.
It gathers the IP address and the round-trip time for every router until the packet finally reaches the destination.
So if your traceroute output shows replies from the first 7 routers, and then suddenly you just see asterisks for hop 8.
You found it. You have just pinpointed the failure to either router 8 itself or the link between router 7 and router 8. Pure isolation.
Okay, we've used ping to see if the network is working, traceroute to find where it's broken. Now we have a location, but we need to get inside that broken device to see why.
And that's where we move to management tools. Telnet, or, much better, the encrypted standard, SSH.
Usually you just SSH in from your own computer, but the sources detail a really critical scenario where that's impossible.
This is the network rescue operation. Imagine a huge routing protocol failure. Maybe OSPF or BGP is misconfigured, and R1 just can't route traffic to R3 anymore. Your management PC can't reach R3 at all.
But the direct links between the routers, the layer 2 connections, they might still be working.
And we could use those. You create what's called a cascading connection, or a jump chain.
Okay.
First, the engineer logs into R1, which works because it's local. Then, from the command line of R1, they use the iOS SSH client to connect to R2.
And that hop works because R1 and R2 are on a directly connected shared subnet. It doesn't need the broken routing protocol to find its neighbor.
Correct. So now you're on R2. And from there, you can SSH to R3 because R2 and R3 are also adjacent. You're effectively leapfrogging across the network.
You're bypassing the big systemic layer 3 failure by using the local working layer 2 connections.
It's the ultimate workaround. It gives you the access you need to get onto R3 and fix the protocol error, even when the rest of the network thinks R3 is completely unreachable.
That turns the network infrastructure into its own troubleshooting ladder. You repair it from the inside out.
You're using the working parts to fix the broken parts. And the commands are simple. Telnet host, or stosh-l username host. It's a powerful strategy.
Well, that brings us to the end of this deep dive. We've covered the foundational tests with ping and its extended version. We've seen how traceroute uses the TTL trick to find failures, and how Telnet and SSH can be used to get into a fractured network.
And that brings us to the final thought from these sources. Every single successful ping you see, it isn't just confirming connectivity, it's confirming the synchronized, simultaneous success of dozens of hidden mechanisms.
From the physical cables and address learning,
All the way up to complex routing table lookups and silently passing through security rules. So if one simple packet requires all of that to work in perfect harmony, just how much hidden complexity are we relying on every single moment we're online?
it definitely gives you a new level of appreciation for that little exclamation point. Thank you for joining us for this deep dive. Keep sending us your sources, and we'll see you next time.